So to be soluble means capable of being dissolved. And we have two other terms. I need you to know the difference between a solvent and a solute. So I would like you to write solvent and solute here. A solvent is the dissolving medium in a solution. In other words, it is the thing doing the dissolving. If liquid water is involved, typically liquid water is the solvent. It is a very common solvent. And typically, we have more of the solvent than the solute. Okay. We typically have more of the solvent than the solute. The solute, of course, is the thing that is being dissolved. So if we look at something like a saltwater solution, for example, the solute and the solvent, we were just told that a very, very common solvent is water. So if we have salt water, water is our solvent, making salt our solute. The salt is being dissolved by the water. The salt is being dissolved. It's the thing that is put into the solvent that is doing the dissolving, the water. Okay? And right here we have a question that asks, do solutions always have to be a solid dissolved in a liquid, like salt dissolving in water, for example? The answer to that is no. It does not always have to be that way. There are many different types of solutions. We, of course, are going to deal more with the solids dissolving into water in this unit, but you can actually have all sorts of solutions involving all the different phases that we talk about in this class. Okay? You can have a gas in a liquid solution. Can anybody think of an example of a gas in a liquid solution? Yeah, carbon dioxide in what? In water. Carbonated water, basically. Yes. Or dissolved oxygen in water. Great, yes. That's an environmental science answer, for sure. So, yes, you can have something like soda or carbonated water, which has dissolved CO2 in it. So we have a gas-liquid solution where the solvent, of course, is our water, and the solute is CO2. Okay, this is what makes your soda fizzy, is all that dissolved CO2. You can also have things like dissolved oxygen in water. That's really important for environmental scientists to know, because having dissolved oxygen in water is important for organisms that live in like freshwater environments and, oceanic environments, for example. Okay? But soda is one we talk about a lot in this class because it's a very common gas-liquid solution. Okay? Gas solution. Can anybody think of maybe an example of that? It's all around us. Air. It's all around us. The air, or our atmosphere, right? Air is a great example of a gas solution. The solvent is the most abundant gas in the atmosphere, which, spoiler, is not oxygen. Does anybody know what it is? It's nitrogen. Very good, y'all. It is nitrogen, which is a diatomic, so I'm going to write N2. So the most abundant gas in our atmosphere is actually nitrogen. And there are a bunch of other gases present as well, so we could consider those guys the solute. O2, CO2, there's argon, there's other gases as well, but I'm not going to list them all out. Okay. You can also have liquid solutions. You use these in cooking or cleaning sometimes. Vinegar, for example, is a very, very common liquid solution. Vinegar is acetic acid. If you did not know that, vinegar is acetic acid. And so our solvent here, we always put behind acids. What symbol do we always put behind acids, y'all? AQ, which means that it's dissolved in what? Water. Very good. So our solvent here would be water. Our acid is a substance dissolved in water, essentially. That's why we put that AQ behind it. And our solute here is going to be our HC2H3O2, our acetic acid, which when you drop that into water, it makes acetic acid. Okay. And then last but not least, you can also have solid-solid solutions. These do not seem very, like, intuitive. Like, how would you mix a solid? Well, you can melt down some metals, mix them up together, and then have them nice and mixed evenly, and then you can have them solidify again, so they are both solid-solid. So really common solid-solid solutions are alloys, metal alloys, okay? So alloys, such as the alloy made with 14-karat gold. 14-karat gold is an alloy. It's not actually pure gold. An alloy is just a fancy word for a mix of metals. There's lots of different alloys. Bronze is technically an alloy. Steel is an alloy. They're mixtures of metals. Does anybody know why would we want to make a gold alloy? It's cheaper, definitely. Not as expensive. And it's stronger. Very good. Yes. So gold, I don't know if y'all know this, but gold is a very soft metal. If you have like pure gold, it's very malleable, it's easy to bend. Whereas if you have an alloy of gold, you put something else in it that maybe it's a little bit stronger, it can strengthen it. So in 14 karat gold, our solvent is gold. Does anybody want to guess what the solute is? It is another metal. It's not copper, but good guess. It is another transition metal. It is silver. Yes. So, there are some other examples of solutions. Like I said, we mostly talk about, solids dissolving in liquid in this unit, but there are other types of solutions I just wanted to draw your attention to. Any questions on that page before we go more and talk about insoluble things? Okay. So we have another question here at the top of page 3, and our question is, does everything always dissolve in something else? No, of course not. Not necessarily, okay? It depends on the substances that are involved or that we're talking about. We say that substances that are not able to dissolve in something are insoluble. When a substance does not dissolve in a solvent, we say that it is insoluble. For liquids, we do have some special names that refer to the solubility and insolubility of liquid substances in one another. We call that whether or not they are miscible or immiscible, okay? So I want you to write those two words down, and I will spell them out because they're a little weird. Miscible and immiscible. Miscible sounds a little bit like mixable to me, and liquids that are miscible in one another are able to dissolve in one another, or they're soluble with one another. They can mix together and be evenly mixed together. Okay? Immiscible liquids are those that are insoluble with one another. So that's your classic oil and water situation. If you've ever tried to mix oil and water together, they do not want to stay evenly mixed together. They want to separate out into the component oil and water. Whereas something like vinegar and water are miscible. They would love to mix together. They can evenly be mixed together. Okay? Our immiscible liquids, like oil and water, will not mix, but they will separate into layers. I mean, you can try and mix them up. You can get them into like a container. You can shake it real good, but if you set that container back down, they will separate back out unless you have like an emulsifier or something. But we're not going to talk about that. Take a food science class if you're interested in that. And what determines which liquid will be on top of the other liquid is another measurement that we dealt with a little bit earlier in the year. So talk about maybe in your groups real quick so you can come up with what would determine which liquid would be on top when they separate out. Yeah, I hear a lot of people saying it. So, density, right? Very good. So, density. So which one is gonna be on top? The less dense or the more dense, y'all? Less dense. Very good. So when those things separate out, the thing that is less dense will be on top. Okay? Any questions there before we talk about covalent solutes and covalent solvents? Okay. Then now that we have some vocabulary under our belt, we're going to talk a little bit about what happens when you have two covalent substances and how you can determine will something dissolve in another covalent substance or not? Our rule for covalent compounds is that like dissolves like. Okay? So this is a very important phrase I want you to remember. Like dissolves like. And when we were referring to the like, we are referring to, of course, the polarity of a substance. Okay? Like dissolves like. So what that means is that polar covalent solvents will dissolve polar covalent solutes. And nonpolar covalent solvents can dissolve nonpolar covalent solutes. If you try and put a polar and a nonpolar covalent compound together, they will not mix. That is why oil and water do not mix. Oil is nonpolar, water is polar. Water is famously polar. I'm actually going to write that right here. If you remember one thing from this class, remember that water is polar. It's very important in chemistry. Okay? Water is polar. And so, in order to determine if a substance is polar or nonpolar, we are going to have to review how to draw a Lewis dot structure, because looking at a Lewis dot structure will help us determine if a molecule is polar or nonpolar, which will determine if something is like something else or not. Okay? So I'm going to try and break this down, because I know that it has been a while for Lewis dot structures. So for this first example, we're definitely going to take it a little bit slow. We are asked for these examples. We're not going to do every single one because there's about 5 of them, I believe. Yeah, there's 5. We're not going to do every single one, but I'm definitely going to have us do the first 2, and then I'm going to point out a couple things on some of the others. We are told in order to figure out these examples, we need to draw the Lewis dot structure for each of our compounds we're given. We are going to determine if the molecule is polar or nonpolar. And we're going to indicate the type of IMF present in each of our compounds. We have a little chart up here to help us when we get to that step. And then we're going to indicate whether or not the following dissolutions will occur. So we're going to figure out, is phosphorus tribromide soluble in water or vice versa? We're going to be able to figure that out by drawing the Lewis dot structure and figuring out the polarity. So for the first step, we're going to draw the Lewis dot structures for each of the compounds. In order to draw the Lewis dot structures, what would probably be a good thing to have from these names, y'all? What would we probably want to write down? What did I just write down? Water. Water's formula, right? Oh. Yeah, water. It's water. Water's formula. So we do need the formulas for these guys. So H2O is water, of course. What's phosphorus tribromide, y'all? Not K. P. There you go. Potassium is K, yes. P, B, R, and then what does that tri mean? 3. So we've got 3 of those. Okay, so there's our formulas. We're going to draw a Lewis dot structure for water, and we're going to draw a Lewis dot structure for phosphorus tribromide. So, I'm going to write out my elements over here, because as a reminder, when we draw a Lewis dot structure, we want to know how many dots we're allowed to draw. Okay, so a great way to figure out how many dots we're going to draw is to write out the elements that are contained in here, figure out how many elements we have of each, how many atoms we have of each element. How many hydrogen do we have, y'all? 2. And oxygen? 1. Very good. Okay? And to figure out the amount of dots we can draw, we're going to have to figure out the number of valence electrons. So looking at hydrogen on our periodic table, can y'all tell me how many valence electrons hydrogen has? 1. That is correct. How did y'all know that? Because it's in the first group. Everything in the first group has 1 valence electron. Okay? What about things like, oxygen that are in group 16? 6. Very good. Oxygen has 6 valence electrons because it is in group 16. Okay? So hydrogen, 1 valence electron, and oxygen, 6. Okay? So we have 2 valence electrons coming from hydrogen and 6 coming from oxygen. So in total, I get to draw 8 dots for my H2O. Okay? So I have my formula. How do I figure out which one of those atoms is going to go in the center, y'all? Do you remember? The one that has less, yes. So looking at oxygen versus hydrogen, oxygen only has one. There's only one oxygen in H2O. There's two oxygen and hydrogen. Another thing is, as a reminder, is hydrogen does not like to be a central atom, okay? Hydrogen was one of our exceptions. Do y'all remember how many electrons hydrogen needs? 2. Hydrogen only needs 2 electrons to be happy, okay? So it's not going to want to hang out in the middle where, we would be drawing a bunch of lines and adding more than 2 electrons to it. So our oxygen is going to be our central atom here. And we're going to draw our peripheral atoms around the central atom. So those are our H's. I'm going to go ahead and do that. And I'm going to go ahead and bond the H and the O here. I'm going to put the bond here. Does anyone remember how many electrons are represented by that one line? 2. Very good. So I have at this point drawn how many dots, technically? 4. So there are 4 electrons contained within both of these. So 2 here and 2 here. So we've used 4 of our 8 dots. You could have also drawn, if you wanted to, you could have done this. That is also fine. Okay? I'm just lazy and like to use my little lines to show my single bonds. Okay? But since we've drawn 4, where would we want to put maybe the other 4? On O. Because how many electrons does oxygen want? It has 6 to start with. It has 6 valence electrons. But how many would it like to get to? 8, or octet rule, right? So if we put 2 lone pairs on this guy, and as a reminder, we want to make sure that we draw them in pairs. We put 2 lone pairs on that guy. Does oxygen have 8 now? It does. 2, 4, 6, 8. Very good. So that is water, okay? That is our Lewis dot structure for water. Let's go ahead and draw the Lewis dot structure for phosphorus tribromide as well, and then we can start moving on to our next steps. I'm going to just get rid of this so I can make a little note about how many electrons I can draw over here. So same thing. We know we have 1 phosphorus and we have 3 bromine. I'm going to go a little bit faster on this one. Okay. For our phosphorus, how many valence electrons do we have? 5. Very good. So there are 5 dots that we can draw because we have 1 phosphorus. How many valence electrons does a bromine atom have? 7. Group 17, we've got 7. 14, 21. So we have in total 26 dots we can draw. Okay? So again, if we use our rule that y'all told me about, putting our central atom, making it the one that has the least amount in the formula, in this case, what would our central atom be? Phosphorus. Very good. So we have phosphorus, and then we're going to put our peripheral atoms around phosphorus. So at this point, we've drawn 2, 4, 6 of our electrons. We have 20 more to distribute. Do y'all remember, do we distribute them around the peripheral atoms first or the central atom first? It is the peripheral. Very good. Good memory, y'all. It is the peripheral atoms first. And how many are we going to try and give our peripheral atoms? 8. Very good. 8. So they already each have how many? 2, because they're sharing in that bond, right? They already each have 2. So at this point, we've drawn 6, 2, 4, 6, and then I want to make sure that each of these has 8. So we've got 6, 8, 10, 12. This guy has 8 now. 14, 16, 18. Bless you. 20, 22, 24. Are my bromine all happy now? They are. They've all got 8. So where do we want to put those last 2? On phosphorus. Very good. That is our Lewis dot for phosphorus tribromide. What questions do we have so far? I know that's a blast from the past. Okay. Then let's go ahead and do step 2. Determine if the molecule is polar or nonpolar. Does anybody remember how, looking at a Lewis dot structure, we were able to determine that? Arya? Symmetry. It's kind of like symmetry. I would caution you to think of it as a little more than just symmetry. Symmetry is typically a great way to look at it. But if I look at a molecule like water, which looks pretty symmetrical, like if I were to, do this, it looks pretty much the same down the middle. The thing about water is, what did we say about water? Water is polar. So what you're going to look at is you are going to look at a central atom, and symmetry will play into it. If you have something that looks the same all the way around, then it's going to be nonpolar. But if you have something like water, which has, 2 hydrogens here, but it also has some lone pairs, if you have a lone pair on the central atom, then you are going to be a polar molecule. Okay, we have some bonds here, but we also have some lone pairs. Water, if you were to actually draw it a little bit more accurately, it would actually look like a little more like Mickey Mouse, exactly. Okay, so there's like our, if you want to consider it Mickey Mouse, it's kind of like Mickey Mouse, right? A lot of people will draw water like this being oxygen and this being hydrogen. So our water, these lone pairs actually have the effect of pushing those hydrogens down, and so we have kind of a weird bent molecule shape. You don't have to remember Vesper shapes for this unit, but you will if you take AP Chem. So still going to need to know how to draw those if you go into AP Chem. So this guy is going to be polar. It's polar because it's not the same all around the central atom. Okay, it's not the same all the way around the central atom, aka there's lone pairs on the central atom. Okay. Because there's lone pairs on our central atom here, we have ourselves a polar molecule. That's what those lone pairs will do to that. That will make it polar. So what are we going to go ahead and assign polarity-wise to phosphorus tribromide, y'all? Polar as well. Phosphorus tribromide also has a lone pair on our central atom. This guy is also polar. Okay? So they are both polar. And let's just skip to step 4 since we did just assign both of them polar. If we know that they're both polar, will they dissolve in one another? They will. They will. Like dissolves like. Polar solvents will dissolve polar solutes. You're not told which one's the solute or the solvent, but you do know they're both polar, and so they will dissolve, or they will mix. So this is a case of these two things being soluble in one another. So that's step 1, 2, and 4 taken care of. Do we have any questions before we review IMFs real quick? Okay. Then let's go ahead and review IMFs. Remember that IMFs, do y'all remember what IMFs stand for? Intermolecular forces. Very good. Intermolecular forces. So our intermolecular forces are going to be our forces that are kind of holding these substances together when, you have a bunch of water with a bunch of other water. The forces that are holding the water molecules together are the intermolecular forces, okay? And the intermolecular force will depend on the type of compound. If you have an ionic compound, the dominant intermolecular force is the ion-ion IMF. If you have a polar covalent compound where H is bonded to an F, an O, or an N, then the dominant IMF is hydrogen bonding. I like to remember that. I remember the phrase, hydrogen bonding is fun. I know it's a little corny. Hydrogen bonding is fun, but replace the U with the O. If you have an H bonded with an F, an O, or an N, H bonding is the dominant IMF. If you do not have an H bonded with one of these elements, and it is polar, then you just have dipole-dipole as your dominant force. And any non-polar covalent compounds, the dominant force is going to be London dispersion. Okay? So, looking at water, water is a covalent compound. We just said it was polar. so it has to be one of these polar covalent compounds. Do we have an H bonded to an F, an O, or an N? Yes, we do. So our most prevalent IMF here is going to be H bonding IMF. What about this polar covalent compound? What is the dominant IMF there, y'all? It's dipole-dipole. It is. Yes, dipole-dipole IMF. Okay. Right? It's polar covalent, but it doesn't have an H bonded to an F, an O, or an N, so it has to be one of our all other. Oh no. Okay, we're back. So it has to be the dipole-dipole IMF as our dominant force there. Okay? What questions do we have about that example? Any of those 4 steps? Okay. For this next one, I would like to challenge you to draw the Lewis dot for ammonia as well as bromine. Remind me, y'all, is bromine diatomic or not? It is, right? It is diatomic. So there's going to be 2 of these. This is going to be, these are covalent compounds, so use the same process we did up here. You're just going to bond these 2 together because you have 2 of them. Just, start off your bromine like this and figure out what goes around the rest of it. I'll give you a couple minutes. Try and do parts 1, 2, 3, and 4, and then we will go over it. Okay, let's go ahead and start going over this one. I'm going to draw out these and have y'all, check your structures against mine. So double check that this is what you got. You may have written out off to the side your numbers to better accommodate. And remember to make sure you draw your dots. Does anyone have any questions about how we drew those? Okay. So our next step after we've drawn our Lewis dot structures is to determine if the molecule is polar or nonpolar. Hopefully you were pretty easily able to do the ammonia one. The bromine one might have needed a little bit more thinking. But the ammonia one, do you all think that this is polar or nonpolar? If you think it is polar, I want you to give me a thumbs up. If you think it is nonpolar, I want you to give me a thumbs down. Yeah, very good. It is polar. Good job, y'all. That is a polar compound. What about liquid bromine? If you think that one is polar, go ahead and give me a thumbs up. If you think it is nonpolar, give me a thumbs down. Very good, y'all. It is nonpolar. This is nonpolar. So this is a case where it's fairly reliable for you to look at the symmetry of the molecule. In this specific case, you have a bromine bonded to another bromine. So these things, they both have the same electronegativity. So remember that polarity is simply a result of the fact that there's an uneven sharing of electrons, okay? But if you have bromine, which bromine has a electronegativity value of 2.8, you have 2 bromines together, they're both going to have the same pull on those electrons. This guy is not going to pull more strongly on the shared electrons than this one is. They're going to pull equally, so it's going to be like a tug-of-war match where these guys are evenly matched, okay? They both have the same pull on the shared electrons, okay? So non-polar, we're not going to have any poles results. No partial positive, no partial negative side because they're both bromine. Does anybody have any questions about that? Need any more clarity? Okay. Non-polar, they're sharing the electrons equally, okay? So as our review, again, we want to indicate the type of IMF present in each of the following compounds. So what did y'all go ahead and assign as the dominant IMF in this ammonia? Hydrogen bonding, very good. Hydrogen bonding. Hopefully you were able to see that there was an H bonded with an F, O, or an N, in this case an N, right? H bonding IMF is our dominant IMF. Okay? And for this guy, as a nonpolar molecule, what is going to be the dominant IMF, the only IMF present? London dispersion. London dispersion IMF. Okay? Any questions there? So, if we have a polar and a nonpolar, are they going to be able to dissolve in one another? No, they aren't. This is going to be an insoluble case. These two things are not soluble in one another. Any lingering questions there? Okay. Then let's go ahead and come over to this page. What I wanted to show you is I didn't want to sit here and do all of these with you because I don't think that's a productive use of our time today. We have a lot of other stuff to get to. But I did want to point out something with this methanol and something with pentane/hexane, okay, how to draw this methanol and how to draw this pentane here, okay. What they did here when they gave you the methanol here, methanol is not a compound that we want you to memorize how to draw. If we ever asked you to draw a Lewis dot for this, we would give you the formula. And what they did in this formula is they gave you a hint to how this structure should be drawn. They're basically telling you that this CH3 is going to kind of be one part of the molecule, and this OH is going to be another part. So I'm going to draw out this molecule to illustrate what that looks like. You're going to have a C bonded to 3 H's, and then the C is also bonded to an OH group, okay? And so the H, this other H over here, it's not with these 3 H's here. This H is going to be off of the oxygen. It's going to be sticking off of the oxygen. Sometimes when organic chemists get lazy, they will literally just draw like, and y'all are not in an organic chemistry class, of course, but sometimes they'll just draw like this to show that there's just this little group hanging off over here, okay? So how we would draw that as a complete Lewis dot structure is, of course, with the O bonded to that central carbon and then the H sticking off of that O, okay? It wouldn't make sense to put the H in between anyways because H can only have how many electrons, y'all? 2, right? But if we were to actually do this math out to see, how many dots do we want to draw, let's double check, make sure we're not drawing too many dots, don't have too many bonds here. I have 1 carbon. I have, in total, I have 3 plus 1, I have 4 hydrogen with 1 valence electron each. I have 1 carbon with 4 valence electrons, and I have 1 oxygen with 6 valence electrons. I want y'all to see that you have a total of 14 dots you can draw. How many have we drawn so far by including these bonds, y'all? 10. Exactly. Where would it probably make the best sense to put those last 4? On the oxygen, exactly. So that is where we would put them. So that is what the Lewis dot structure of methanol looks like. Again, the way that they wrote the formula out is to kind of hint what this should look like. You're going to have CH3 kind of clumped together, and you're going to have your OH off to the side. Yes, ma'am? So carbon loves to be central, okay? So in this specific case, like you don't want to make oxygen the central atom because then putting the OH off to the end, and sorry, I guess I should probably say this because it probably didn't show up on the recording. So I had a question that was, she was asking, how would you know what the central atom is if you got another formula that was something like methanol? The answer to that is carbon is typically going to be your central atom on something like this because carbon loves to be central, and you would not write this OH off to the side if this oxygen was going to be your central atom, okay? This is telling you that this is basically hanging off as a little kind of addition over here, and carbon, you can think of C for central. Carbon loves to be central. And so you, in a lot of these organic compounds, you basically see something like a carbon backbone, and that will hang out in the middle then. Does that help? Yeah? Okay. Any other questions? That was a good question. Okay, so you have something like methanol there. Again, that's kind of a more complicated organic substance that you're not going to see too much. You might see something like that on your practice worksheet, but it's not a super common thing that shows up in this class a lot. Okay. So looking at this compound, kind of consider our carbon to be central is our atom, and so we do have a case where we have an oxygen over here as well as some H's over here. So would we classify this guy as polar or non-polar? What do y'all think? Is actually going to be polar, okay? So this little OH over here off to the side, you have an H, you have an H, you have an H, but you don't have an H bonded to the carbon over here. You have this oxygen. So what's actually going to happen here is you have this little OH group over here, and since you do have an oxygen bonded to an H, what type of IMF is going to actually be able to happen between, one methanol atom or one methanol molecule and another methanol molecule? Hydrogen bonding. These methanol molecules, if you started putting them in, a big thing with other methanol molecules, they could actually engage in hydrogen bonding. And spoiler alert, hydrogen bonding only really happens with our polar molecules. So there you have that. So I just wanted to show you how you would draw something like methanol, since that's probably not super intuitive. It's not something that you would just think up on your own a lot of the time. The other thing I wanted to review is how we could draw something like pentane. We did give you pentane and hexane, some like organic molecules like this, back when we were in our Lewis dot structure unit, but I realized that it has been a while since we have talked about Lewis dot structures. So I wanted to show you how to draw another organic molecule like pentane or hexane. You, of course, want to write out the formula first so you know what you're kind of dealing with. Does anybody remember what the formula for pentane is? The C5H12. Very good. C5H12. So the pent means 5. We have 5 carbon. You do 5 times 2 plus 2 to get the 12 hydrogen. For something like pentane or hexane, all you're going to have here is the carbons are going to form a backbone of this structure. Okay? So you're going to have 5 carbons bound to one another. So I'm going to draw a chain of 5 carbons. And if you are dealing with something like pentane or hexane, then the hydrogens are going to be all around. And if you actually fill in so that, every single thing has 8, 2, 4, 6, 8, 2, 4, 6, 8. So everything has 8 shared electrons. You fill in hydrogens all around these guys, you'll actually find that you will get 12 hydrogen. It's really, you don't even have to count them. But if you did, you would see that there were 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 hydrogen. So it's a lot of C's and H's. But that is how you would draw something like pentane. With hexane, very similar. You're just going to have 6 carbons instead of 5. Okay? And when you get pentanes, hexanes, things like this, these guys are going to be nonpolar. Okay? These guys, there's not going to be a more strong pull of electrons, in any which way. So there's not going to be any pulls being created. They're going to share these electrons fairly equally. Okay. Carbon and hydrogen have very similar electronegativity. Carbon's technically a little bit more electronegative, but not enough that it's going to really pull on those super hard. Okay? What questions do we have there? Okay. Then we're going to go ahead and move on to, I'll let y'all, go and do these. If you want to check with my key later, you can come check with me. But you can do those for practice. I wanted to just highlight those since those are a little bit weird, something you may not remember as well. What I want us to move on to, though, is how we can illustrate the dissolving process, or what it would look like for a polar covalent solute to dissolve in a polar covalent solvent. Okay? So with that, I want to remind us what is happening in a polar covalent compound. We assigned water, we said that water was a polar substance. The reason why water is a polar substance is because of an unequal sharing of electrons, okay? So I want to remind us about these funky little symbols. We've got this kind of little, it looks almost like a fancy looking D with like a little hook at the top. And then there's like a little negative here, and then this one is another little fancy one with a little positive symbol, okay? So we drew that like that because oxygen is a atom with a higher electronegativity value than hydrogen. It's so much higher than hydrogen that we consider oxygen to be a electron hog here, okay? So it is hogging all of the electrons, essentially. The larger electronegativity is such that there is more pull on the shared electrons from oxygen than there is from hydrogen. So we end up with some poles. We have a partial negative pole up here because the electrons are hanging out more frequently around oxygen because of its pole. And there's a partial positive down here because hydrogen doesn't have as strong of a pull on those electrons because it's less electronegative, okay? So this guy's less electronegative, this guy's more electronegative. As a reminder, you have this on your page 7 as well. As a reminder, electronegativity values, we have this electronegativity trend that we can consult. We have specific electronegativity values that you would be given if you needed them. Otherwise, you could just look at the trend in the periodic table. Fluorine is the most electronegative element. Okay. Remember that fluorine is the most electronegative element. So our trend is such that when you go to the right and up the periodic table, you get more electronegative. Okay? So these guys don't have any electronegativity. They're not trying to pull any electrons towards themselves. They already have 8. But fluorine is real close to having its 8. So it's going to have a whole lot of pull on any electrons that it's sharing in a covalent bond. Okay? So be aware of your electronegativity trends. Please remember that. It will help you out. We know that water is polar, that it is going to have, oxygen is going to have a greater pull on those electrons. And so if we wanted to illustrate the dissolving process, the interactions that would result between phosphorus tribromide and water, we could do that by drawing out our Lewis dot structures and showing which side has the partial positive and which side has the partial negative pull. We did these Lewis dot structures. We drew them on the previous page. That was our first example. So I'm not going to, go through real quick about how to draw those again. I'm just going to draw them out. I am going to draw out real quick the Lewis dot structure for phosphorus tribromide so I can show you which side is the partial positive and which side is the partial negative on this polar molecule. Okay, there's our phosphorus tribromide. Okay, I'm going to go figure out the electronegativity value for phosphorus as well as the electronegativity value of bromine. So the electronegativity value, and I will flip this back here in a second, the electronegativity value for phosphorus is 2.1. The electronegativity value for bromine is 2.8. So since our electronegativity for this guy is 2.1, and this guy is 2.8, who is going to have a stronger pull on the electrons in these covalent bonds? Bromine. Very good. So our bromine will be our partial negative pole. These bromine. You could draw them on each. I'm just going to draw it on one. And then this will be our partial positive. Kind of do that there for a second. And then I'm going to use two different colors to illustrate the interactions between the two different molecules, the water molecules and the phosphorus tribromide. We are told to show the attraction between the different poles of the molecules, and we want to draw at least two of each type of molecule. So we want to make sure we're following our instructions. It's going to be a little bit tedious to draw this many, but we're going to get through it. So let's go ahead and draw ourselves a phosphorus tribromide. And this is not a very good marker. I'm going to switch one out. Maybe I'll do this. That's better. Okay. Let's go ahead and do a little red. Okay. Okay. So sorry for the marker color switch, but I'm going to draw that guy in red. This is our phosphorus tribromide. As a reminder, this phosphorus atom is the partial positive pole, and this bromine is the partial negative pole. So if I go to draw a water and how it would orient itself with this molecule, we would have water, the hydrogen would be facing, this partial positive hydrogen would be facing the partial negative bromine in that molecule. Okay, so there's water. Now I'm going to tell you right now, you should just memorize how to draw the Lewis dot structure of water. We use it so much. Just remember how to draw that little Mickey Mouse guy. And what we can do is we can actually show the attraction between this hydrogen, this partial positive hydrogen, and this partial negative bromine by drawing little dashed lines, okay? So this is an intermolecular force. You are going to represent intermolecular forces with a dotted line only, okay? This is not a covalent bond that is forming. This is a force that exists because of the attraction of this partial positive pole and this partial negative pole. It is a force. It's not a covalent bond. So I'm just going to do my little dashes to show that that is an intermolecular force. I'm going to zoom in a little bit more so it's easier to see. There are inter and there are intra. So this covalent bond is an intramolecular force within the molecule of water. This is an intermolecular force between the hydrogen of the water molecule and the bromine of the phosphorus tribromide molecule. Inter, yes. When we're using IMF to mean intermolecular force here. Yes. Because we typically refer to intramolecular forces as ionic or covalent bonds. Yeah, so this is intermolecular force. Okay? We want to draw two of each type of molecule. So again, I'm gonna go ahead, I'm gonna draw the P over here so it's close to my oxygen. Because remember, the P is the partial positive on this molecule. Draw myself another phosphorus tribromide molecule. There it is. Okay, remember these are the partial negative poles, these bromine. The phosphorus is the partial positive pole. So we can have another IMF here. No solid line, please, only a dotted line to show the force. And then we can show, one more hydrogen, one more partial positive pole. There's another IMF. So I drew 2 of each type of molecule. I made sure that my hydrogens and my bromines were shown to be attracted to one another, since those are my partial positive and negative poles. Or that my phosphorus and my oxygen were attracted to each other. Because again, partial positive, partial negative, the positive and the negative are attracted to one another, opposites attract. What questions do we have here? I realize I smeared this pretty bad. There is a better picture. Okay? Okay. And if we don't have any questions there, I can move on to our ionics. Is anyone still using what I have on the board? Cool. Then let's go ahead and talk about how we can figure out if an ionic solute will dissolve in a covalent solvent. Okay? We were just talking about covalence, dissolving in covalence. Now we're going to talk about ionics and whether they can dissolve into covalence. For ionic compounds, the ability to dissolve is going to depend on the properties of the covalent compound. The first thing you need to know here is that ionic compounds will only dissolve, in polar covalent compounds, polar covalent substances, okay, or solvents. Ionic compounds will only dissolve in polar covalent solvents. So if you have an ionic compound and a non-polar solvent, and they're like, will they dissolve? You can immediately say no, because it has to be a polar covalent solvent, like water, for example. Okay? Water is our most common polar covalent solvent. There are other ones like ammonia and stuff, but water is very, very commonly used. Okay? If you have an ionic compound and a polar covalent solvent, and they say, hey, do these dissolve in one another, you cannot just automatically say yes, okay? Because some ionic compounds are insoluble. You may remember our handy-dandy solubility chart from a couple units ago. It's all coming together. It's all coming together, right? This guy, you still do not have to memorize it, but you still do need to know how to use it, okay? So if you are dealing with an ionic compound and you have water, water is the most common polar covalent solvent. The most common polar covalent solvent. You can look at this chart to figure out, yes, it will dissolve, or no, it won't dissolve. These soluble compounds, of course, are these guys that have this AQ symbol, and our insoluble ones are our solids, okay? So if the compound is soluble, it will get the AQ state. Do you remember what AQ is short for? Aqueous. What does aqueous mean? It's in water. It's dissolved in water, okay? The reason why we wrote aqueous next to things is because we were trying to say that they are dissolved in water, okay? If they are AQ, okay, they will dissolve in water. If a compound is insoluble, that means it will not dissolve in water and will form a solid substance called a what? Starts with a P. Precipitate. Okay? These were our precipitates when we talked about, things precipitating out of solutions. So what symbol did we put next to precipitate, y'all? S. S for the solid state designation. Okay? So we can figure out, is this ionic compound going to dissolve in water by using this chart, just like we've used it in previous units. A little note about water. Since water is so good at dissolving so many things, it can dissolve other polar covalent molecules as well as a ton of ionic compounds, we will call water oftentimes the universal solvent. Water is really good at dissolving things. We call it the universal solvent because it can dissolve other polar covalent molecules as well as a ton of ionic compounds. Not all ionic compounds, but a whole lot of them. So I would like y'all to spend a couple of minutes trying to refresh your brain on how to use that solubility chart. Figure out if you would put an AQ or an S next to all of these compounds here. So spend a couple minutes doing that. We'll check our work, and then we will move on to the next page, and then we're almost done. Okay, go ahead and check your work against the board. Do y'all have any questions before we talk about how to illustrate this dissolving process? Okay, so those are the answers there. If you flip to page 6, you will see some diagrams as well as some other blanks we're going to fill in. So we are going to fill in these blanks, kind of look at this diagram, and then illustrate our dissolving process for the example we are given. So the first thing I want you to do is write dissociation in this top blank. Dissociation is the process of a compound separating into its ions when you dissolve it in a polar solvent. And it does this in a reversible manner. This is why when you dissolve salt in water, for example, you can evaporate the water and then get the salt back, essentially. Because it can separate out into ions, and then those ions can come back together if you take the polar solvent away. Acids, bases, and ionic compounds, a lot of ionic compounds, not all of them, can undergo dissociation. Even the ones that we consider to be insoluble, a lot of them will undergo a little bit of dissociation. We just have you write a solid next to them anyways. Okay, so dissociation is going to happen when the bond between ions is weakened due to the formation of new intermolecular forces with the polar solvent. And so what you see is new IMFs will form. These IMFs are called ion dipole IMFs. You'll talk a lot more about IMFs when you get into AP Chem if you choose to take that. We're just going to kind of define this as an ion dipole IMF and not go super into it beyond illustrating this dissociation process. Okay. And one thing to note that I will emphasize again later is that our polar covalent compounds, while polar covalent compounds can dissolve in other polar covalent compounds, they do not undergo this process of dissociation, okay? They just do this thing. They just interact with the solvent in this way. They won't actually separate out into ions because covalent compounds do not consist of ions. They are sharing electrons. But when we look at ionic compounds and polar covalent compounds, we will show the ions forming as this compound is dissociating, okay? So when we illustrate this dissolving process, we're going to basically show some water molecules around the ions oriented in such a way that the partial positive and negative poles are lined up with the opposite charge of whatever ion they are being attracted to at that moment. So what we see here, for example, when sodium chloride is dissolved, is we have some water molecules. The oxygen portion of the water molecules will face the sodium ion, since sodium is a cation, a positively charged ion. The partial negative of the oxygen in this molecule will be attracted to the positive of this ion. Okay? The opposite's happening over here with the chlorine. The chloride ion has a negative charge, and so the partial positive poles of the water molecule will be attracted to the negative chloride ion. So if we wanted to show the dissociation of potassium bromide, we could show that by drawing out the ions that make up potassium bromide as well as the Lewis dot for water. So that's what we're going to do. I'm going to have us draw out water again, which, as a reminder, if you have this guy memorized, how to draw it, it will make things a lot easier. Remember that hydrogen has that partial positive charge, and oxygen that partial negative charge, because oxygen is much more electronegative than hydrogen. And then this is going to be kind of another blast from the past. When you draw a Lewis dot for a ionic compound, we are going to use our brackets, okay? So this is not, we're not going to go like this and try and show them sharing electrons. That is not what happens in an ionic compound. The reason that ionic compounds are held together is because you have oppositely charged ions making that up. So do y'all remember what type of ion potassium will form? What charge will potassium get? +1. Yes, so potassium has one valence electron. It will form a +1 ion when it loses that valence electron, right? So potassium is going to lose its one valence electron, so we're not going to draw any dots around potassium to represent that it has lost its one valence electron, and it takes on that +1 charge. Bromine, on the other hand, how many valence electrons does bromine have? It has 7 valence electrons, so it will take on a -1 charge, right, when it gains that one that it needs. So bromine is going to gain 1. Okay, so it's going to have 8 valence electrons. It's going to take on that -1 charge when it takes the valence electron from potassium. So you'll remember back in our formula writing unit, remember when we made potassium bromide, right? Okay, there's one of each because you just need one of each to cancel each other out via the charge. Okay, so when we put these two things in solution together, when we put them together in the solution, okay, we're going to end up separating out these ions. We're going to have our potassium ion, and then we're going to have our bromine ion. And then we're going to draw the waters around them so that it matches up with this idea up here of the opposite charges attracting. So we know that this is a partial positive pole on this water, and this is a partial negative pole on this oxygen. So which one do you think I should have facing this positive potassium ion? Should I have the H's face it or the O face it? The O. Very good. Opposites attract, y'all. So we're going to draw these like this. You don't need to include like little lines. If you want to include lines between them, you can. But you can just show that the O's are going to be like that around it. Whereas the bromine, what's going to be attracted? Which side is going to be attracted to the bromine ion, the bromide ion? The hydrogen, the H's, right? Okay. So there's my waters there. Okay. What questions do y'all have about that? So we essentially just talked about like 3 different scenarios in terms of things dissolving today. Okay, that's what we spent a lot of time today talking about 3 different scenarios of things dissolving or not dissolving. So on the next page, I want to go ahead and summarize what we went over today, so we just kind of make it a little bit more concise, something easy to flip to and look at. Is anybody still using what I have on this page right here? Okay. Now let's go ahead and summarize what we learned today, so I think that'll be easy for you to just flip back here and remember. To summarize our solubility rules, if you have a covalent and a covalent substance, two covalent substances, okay, your rule is that like dissolves like. Remember that like dissolves like. We are talking about polarity when we talk about like dissolving like. Nonpolar will dissolve other nonpolar. Polar will dissolve other polar. Okay? So in order to determine that polarity, you want to make sure you draw out your Lewis dot structures. Draw your Lewis dot structures. There is no dissociation. You are not going to do what we just did with that ionic example. You're not going to show ions forming. There's no dissociation because these are covalent compounds. You are going to instead show oppositely charged poles attract. Okay, one partial positive pole will attract to another's partial negative pole on a different molecule. Like dissolves like, draw the Lewis dot structures, no dissociation, the poles attract. So that was what we did over here. We showed the poles attracting, dotted lines only. We're not forming a bond, it's just an intermolecular force. And so that is what you do when you have two covalent substances, aka two things just made up of nonmetals, right? If you have covalent and ionic substances, okay, if you have a nonpolar and an ionic, this one's easy. Nonpolar and ionic compounds are not soluble. They are not soluble in nonpolar covalent compounds ever. Not soluble ever. If you have a polar covalent compound, however, like water and an ionic substance, you need to check your solubility chart. Okay, check your solubility chart. If it is soluble, bless you. If it is soluble, dissociation occurs. Okay? Remember, dissociation is when an ionic compound splits into ions when it dissolves. So that is a short little summary of everything we learned today in simple words. What questions do we have? Okay. Then we are done for today.